Welcome to the first talk on fully rough turbulent flow in pipes on man-made channels. In the next few minutes, we are going to address a few key questions. What is a fully rough turbulent flow? How is it used? What is new since 1933 and why is it relevant today? The background leading to this talk is this series of graphs first presented in 1933 that we will discuss in this video on the next two videos on the same topic. Starting from the beginning, what is a fully rough turbulent flow? First and foremost, it is a turbulent flow that is a flow motion characterized by an unpredictable, chaotic, and quasi-random motion with strong mixing property on a broad range of relevant time and length scales, which is typically observed when the Reynolds number, defined in terms of the cross-sectional average velocity on the equivalent pipe diameter, is greater than 3 to 10,000. In the context of a fully rough turbulent flow, the flow resistance and velocity distribution are further functions of the relative boundary roughness only, without any effect of the Reynolds number or any dimensionless discharge. Example of fully rough turbulent flow are shown here, with a pebble bed channel on the right and a channel on the left with some industrial rubber mats on the floor. The context or the notion of fully rough turbulent flow derived from a series of experiments first published in 1933. Experiments performed at the Göttingen University in Germany under the supervision of Ludwig Prandtl, showing on the vertical axis the flow resistance as a function of the Reynolds number, horizontal axis, and relative roughness corresponding to the different symbols. And for large Reynolds number, we can see that the flow resistance reaches a horizontal asymptote, meaning that the flow resistance becomes independent of the Reynolds number, being only a function of the relative roughness height. These experiments were conducted by Nikuradse with detailed measurement of pressure loss and velocity profile in pipes with internal diameter from 24 to 99 millimeters, using water on uniformly distributed sound grain size ranging from 0.1 millimeter to 1.6 millimeter. The results of Nikuradse in terms of the flow resistance were first presented in this form of graph for fully rough turbulent flow, whereby the flow resistance was a function only on the relative roughness height, result widely accepted today and which has been extended. Indeed, if we looked at a presentation of the same dataset with the Darcy-Weisbach friction factor on the vertical axis, the relative roughness height on the horizontal axis, we can see the dataset of Nikuradse, 1933, together with a correlation that he proposed, and more recent experimental data, including superpipe data. In 1933, Nikuradse proposed this empirical formula to characterize the flow resistance in fully rough turbulent flow. Flow resistance formula, which has been since extended thanks to further new results, and is valid with up to Reynolds number of 7 10 to the 7. It is important to note, however, that there remain some discussion in the definition of the equivalent sound roughness height, Ks. Nikuradse used a mono-size sound roughness grain size, while for more recent data, like the superpipe data, the equivalent sound roughness height was defined as 3 times the root mean square of the surface rugosity. Another part of the experimental dataset of Nikuradse and fully rough turbulent flow are the velocity distribution in pipes, which will be discussed in the second part, in the second movie. Let's acknowledge the contribution of German scientists on fully rough turbulent flow, in particular Ludwig Prandtl and his former PhD student you are Nikuradse. In summary, fully rough turbulent flow are turbulent flow for which a Darcy-Weisbach friction factor on the velocity distributions are function only on the relative roughness on a 1933 formula presented by Nikuradse is still valid and has since been extended both in terms of a broader range of relative roughness height and range of Reynolds numbers. Relevant bibliography. Thank you very much.